Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is part of the great stuff. This is the AAS Journal Author Series. And I am delighted to have Joaquín Espinoza-Troni with us today. Hello, Joaquín.
Hello, thank you for the invitation.
Well, thank you very much for agreeing to talk about your very awesome article, which we will get to here in a little
Yeah,
bit. And Joaquín, what is your geolocation?
I am in Chile in this moment, Santiago.
So we are in our winter mode there in Santiago.
Yeah, but it's not a bad winter.
Yeah, well, okay. Very good. And it is July 22nd of 2025 as we record this, and I'm in Phoenix, and we are definitely not in our winter mode. We're in
Yeah.
our definite summer mode. So we're getting the rains, the moisture. Yeah, it's really good. Cool.
That's great.
And Joaquin, what do you like to do for research?
Well, I do research in space plasmas. My usual work is in Ponder motive force, in application in space phenomena, but the article that I will present at this moment is a different topic that I was not used to, but is magnetic holes.
Mm-hmm. Well, it's related, right? It's not terribly far.
No, yeah, but yeah, it's not what I usually do.
Very good. And that is going to bring us to this very awesome APJ article. It is open access. It's the open access era, people. You can go grab a copy for free. Go get one.
Yes.
Electron-scale magnetic holes generation driven by Whistler to Bernstein mode conversion in fully kinetic plasma turbulence. And Joaquin, take us away.
Well, this paper was in collaboration with Giuseppe Arro, Felipe Asenjo, and Pablo Moya. We made this collaboration during my internship in Los Alamos.
Okay.
Yes, between last year and these months of the year. I just arrived in Chile
Okay.
like a couple of weeks ago, so I was in summer also.
Very good.
Um, okay, and the topic of this research is about trying to understand the generation mechanism about the electron scales, magnetic holes,
Okay.
um, in turbulence environments. So specifically in magnetosheath.
Okay. I'm with
Yeah.
you. Hmm.
So, well, to understand, I will begin with what is a magnetic hole. So, magnetic holes are usually found in turbulence. They are like stable coherent structures those are characterized by like deep of the magnetic field.
Hmm.
So it's a very like localized deep, very strong deep of the magnetic field, and they were first like observed by Turner in 1977 in
Okay.
the solar wind, and since that time there had been observed in a lot of different space environments.
Yes.
We can talk about, for example, the solar wind,
Hmm.
the magnetosheath, in comets, even in magnetospheric scarps. And
Cool.
basically they're uh,
Everywhere.
everywhere. And I mean, in space, usually plasmas are in turbulent environments. So
Uh-huh.
yes, we will see that during this paper that turbulence can drive the formation of magnetic holes, so it makes sense that we can find those magnetic holes in those types of space environments.
Cool.
Well, these holes can exist in different scales. They can have like in MHD scales, like 100 of ion zero radius,
Uh-huh.
or we can go to even very kinetic scales, small scales as a couple of electron year radius.
Okay.
Uh, and the magnetic hole actually of these studies of those scales at kinetic scales. Um, well, these magnetic holes have different, they're not only characterized by the deep of magnetic field, also usually have a lot of temperature anisotropy. In the case of the huge ones,
Okay.
is ion temperature anisotropy. In the kinetic scales, the ion are demagnetized, so we only have the electron temperature anisotropy.
There we go. I'm with
Um,
you. Hmm.
These kinetic scale magnetic hole lately have been like more relevant because with the magnetospheric multiscale mission (MMS), there has been the possibility to measure them. So there has been lately a lot of measurement of observations of electron scale magnetic holes, especially in the magnetosheath. So uh, yes, so can you go that down the
Go
paper?
ahead.
Yeah,
Yeah, yeah,
yeah,
yeah.
yes. Yeah. So um, well, so that's why in this paper we will try to um, start with some simulations and or with the magnetic shift simulation. With that, we will try to find how the electron skin magnetic hole is produced because even if these holes have been hugely observed, there has been a lot of discussion of the generation mechanisms that can produce the magnetic holes.
Right.
In this case of the large scale one, um, there is usually a lot of articles and literature that they sustain that it can be because of the mirror instability.
Okay.
So the mirror instability can develop and produce this type of structures.
Okay.
But there is some discussion about that because uh, there has been some simulations and usually in mirror instability excite peaks of the magnetic hole. There is still like a lot of debate in the scientific community about that, but the same with the electron skin magnetic one. They have been proposed that they can be also produced by the field Soulen instability. Um, and but the problem is that for the field Soulen instability, we need that the temperature of the electrons
Yeah.
have to be um, um, I don't remember it had to be cold or hotter, but yeah, it doesn't usually we doesn't found that. And also well, that also there has been lately, especially by Giuseppe Perot, some simulation, some in turbulence about the generation of large scale magnetic holes. There have been found that the turbulence can drive the generation of those large scale magnetic holes, and also of near ion scale magnetic hole. I will say like 2 year radius about that.
Yeah.
So this is the continuation of those works, like the logic continuation until like lower scales. So we are in fully kinetic scales with 5 electron year radius of the scale of the magnetic hole.
Okay.
Um, and there has been also some works, simulations, especially Haynes 2015. In those simulations, they um, start with some turbulence that is a scale of the magnetic holes that are produced. So it's more like a description more than a study of the generation mechanism.
Yes.
It's a description of the magnetic hole, and they can found that they can live stable in turbulence environments. So basically, this study is trying to propose a mechanism. It doesn't have to be the only one, the unique one,
Yeah. Okay.
but is a way to
Fine.
say that the 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 energy from the large scales can cascade until it by different process it can end in the generation of these coherent structures.
Okay. Hmm.
So, okay, that will be like a general introduction. Now we can talk a little about the simulation. The simulation that we will use
Okay.
is a peak simulation. It's a fully fully kinetic simulation of freely decaying turbulence.
Hmm.
We will initialize the turbulence with a perturbations that are like much in larger in scale that the magnetic hole produce. So in
Okay.
that way, we make sure that the magnetic hole is not produced directly by the initial perturbation, but from the energy cascade and the process that and cross-scale interaction that we will see during the paper.
Okay.
Uh, yes, in the simulation also it's important to say we have reduced the mass ratio so of 10 between the ion and electron mass
Right.
um, of 100, sorry, of 10 no, of 100.
10 would be a
And
little big. Hmm.
yeah, yeah, yeah. Yeah, I am bad remember like details.
Well, that's why we write them down in these papers, you know?
Yeah. Well, so now we can continue to the first part of the paper. First, we will characterize the magnetic hole that we will study. So, in figure one, we have for time 15, uh, 500 electron year radius.
Hmm.
In that moment, the turbulence is fully developed, and we have the magnetic hole, electron-scale magnetic hole, where when it's fully developed, so we will see the characteristics that it has that are very general for magnetic electromagnetic holes.
Okay.
So if we go to panel A and B, we can,
Blow these up.
in panel A, we have a big picture of the turbulence. And if we do a zoom on that part, in panel B, we can see the electron scale magnetic hole. As I
There.
said before,
Hmm.
if we see it has more or less like 0.5D uh, DE, so DI,
Okay.
so that's more or less 5D with the reduced electron mass and ion mass ratio. So
Hmm.
it's an electron scales. If we go to panel C, we did the velocity distribution of the
Okay.
black square that is in the panel V.
Yes.
We can see that it has a lot of, the black arrow is the direction of the mean background magnetic field.
Okay.
We can see that it has a lot of temperature anisotropy in the perpendicular direction of the magnetic field. It has like a very unique and very interesting shape because we can see like a mushroom shape
Yes.
and we can see the hat, like two populations, the hat at the bottom of the mushroom. The
Uh-huh.
hat is had a lot of anisotropy, is
Hmm.
more hotter than the bottom, that is more like a cold
Yeah.
population,
Hmm.
and also has like it's empty in the inside. It's like a ring.
Yes.
Um, we can see much better in panels between panels D and F a 2D projection of the velocity distribution. And is more clear in panel E and F the velocity
Oh,
like difference,
yeah.
velocity anisotropy. There we can see the temporal anisotropy that we can usually find in these structures.
Cool.
And now if we do a cut we can see in panel B a cut in the
Yeah.
horizontal cut that pass through the magnetic hole.
I'm with you.
Uh, we plot different plasma parameters over that cut. And for example, in panel G, we have the different components of the magnetic field
Mhm.
normalized with the initial background magnetic field and the magnitude of the magnetic field. As we can see, in all the plots, the gray area is the area where the magnetic hole is found.
Okay.
So
With
we
you.
can see that the magnetic field has like a sharp decrease of amplitude there, of magnitude
Yes.
there.
Yes.
Is mostly in the out of plane direction, is the C direction out of plane.
Hmm.
In and in panel H, we can see also that there is an increase of plasma the electron and ion density
Yeah.
inside the magnetic hole.
Hmm.
Uh, the electromagnetic hole, the electromagnetic hole they trap particles, so that's why the increase of
Oh,
density.
yes.
In panel I, we can see the electron fluid velocity for different components normalized with the Alfvén velocity. We
Yes.
can see that the one of the components is like having like a sinusoidal shape.
Yes.
Yeah. Um, I wanted to say the color of the line, but I am a little color blinded, so like I shoot my my foot with this plot.
Gotta get
Yeah.
a better color map. Okay. But
Yeah,
I'm with
well,
you.
but yes, and this is because we have a ring, like a ring current
Yes.
around the electron-scale magnetic hole. That's why we can see that sinusoidal shape. And it's only the electrons that are
Right.
sustaining that current because as we can see in panel G, the ions doesn't interact very much with the electromagnetic hole, so the
Right.
velocity is not correlated with the path through that region.
Right.
The same with panel L. If we see the ion temperature,
Okay.
the same is that it's not correlated with, but in case of panel K, we can see the total temperature, the perpendicular component of the temperature, and the parallel component of the temperature with respect to the background magnetic field.
Yes.
And we can see that there's an increase of total temperature,
Uh-huh.
an increase of the
Maybe
perpendicular one,
particular one.
and a decrease of the parallel one. So
Mm.
that's why we can also, it makes sense with the velocity distribution that is an increase of anisotropy. And also this increase of temperature and increase of density
Okay.
sustains the balance of pressure because of the decrease of magnetic field pressure. So that maintains this structure in a stable. It can be stable for a lot of time, a lot of hundred of electron zero
Turnovers.
radius.
Uh-huh.
So in time, and in panel M, we can see the current. We can see the electric current. We can see the electron current because of the drift of the E cross V drift,
Yes.
and the electron current because of the pressure drift. We can see that these two currents sustain mostly the total current, the ring current around the electron skin magnetic hole,
Uh-huh.
and that's important. Of course, there is some components because of the inertial tense in the generalized Ohm law and some kinetic effects that were not considered, so that's why it's not matching completely. But
Okay.
this is very important to consider this because later below we will see that it's an important part of the generation mechanism.
Cool.
And in panel N, we can see a plot of the pitch angle under the cut, and we can see that in the part of the magnetic hole, there is trapping. The magnetic hole is trapping a lot of particles with high pitch angles. So the this makes sense with paper of Haynes, where in that description of the magnetic hole in turbulence,
Yes.
uh, the electrons are trapped in or like petal orbits. Uh, the electrons that are trapped also have high pitch angles, so that's why there is increase of anisotropy.
Got it. Mm-hmm. Yes.
Of course, in this paper, we didn't do like a particle analysis of the trajectory that the electrons follow. So
Okay.
we can't say that it's the same trajectories, but it can be an explanation of how it's trapping. And it's just that in this paper, we are trying to focus in the mechanism that is generating the magnetic hole,
Yes.
electron schematic hole. So, well, that will be a general description of the characteristics. These are very common in um, electron scale magnetic holes. Also, in large scale magnetic holes, we have similar characteristics, only that in
Okay.
that case, the ions have importance. So we will see the analog characteristics of electrons, but in ions, so we'll see the ion temperature increasing and
Right.
um, temperature anisotropy of the ions increasing and like that. So, okay, now we can continue to
Okay.
the following panel.
I'm
Uh,
with you so far.
yes, maybe we can skip directly to the panel 3 so we can see the coordinate system that we will use. So
Where
it
we want
will
to
be
go?
easier.
Figure three?
But I mean, figure 3, yes.
Figure three. Okay. Let's pull up figure three. Okay.
Or 4. Better
Four.
4.
Good.
Yeah.
Oh, the geometry. Yeah, yeah.
Yeah, yeah, it's better to start with that so we
Good.
have the coordinate system. So
Like,
this figure is an illustration of the coordinate system that we will use. So
okay.
it C is out of plane direction. The simulation is in the X and a Y plane. Is
Hmm.
at is everything confined in the 2D space, but all vectors and are in have three components of the vector. So they can be also out of plane direction.
Yeah.
So in we have the x parallel, x perpendicular one, and x perpendicular two in that square. Those
Yep.
are the coordinates that are aligned with with the magnetic field direction. And we have also the vector n and vector l.
Yes.
L will be from longitudinal and N from normal.
Well,
Those are longitudinal will be the direction in the direction of the parallel to the magnetic field inside the 2D plane, and
okay.
the N will be in the normal direction with the respect of the magnetic field inside the 2D plane.
Okay.
We will see that the waves that we will study in this paper follow the magnetic field, the lines of the magnetic field. So the longitudinal direction is also in this case, a specific case, the direction of the wave number of the direction of the propagation of the wave.
Yeah.
So
Okay.
okay, now with that coordinate system in mind, we can go to figure 2.
Okay. Keep that in
So,
mind.
okay,
You
so
too.
we started in time 500 with respect to electron U radius.
Hmm.
Now that's the fully developed electroscale magnetic hole. Now we will go back in time just when the simulation starts.
Okay.
So
Okay.
we have these panels in every like row. We have different parameters, and in every column we have in different times. So in the third row, we plot the high pass filter magnetic field in the outplane direction.
Uh-huh.
Um, this high pass filter is in the scale of the electron scale magnetic hole. So we want to see perturbations that are under that scale.
Yes.
Uh, the streamlines that we see are the direction of the magnetic field
Hmm.
in the 2D plane. In the second row, we have the a plot of the electron temperature and isotropy
Okay.
um,
Hmm.
with the streamlines that are the electron velocity, fluid velocity.
I'm with you.
And in the third row, we have the
Which,
angle between the out of plane magnetic field and the in plane magnetic field.
yes.
So in this case, that angle will be the angle between the background magnetic field and the wave direction because the in plane magnetic field is in the direction of the wave.
Yes. Yes.
So uh, in And if we start with the first time, we can see that there is not much perturbation of the background magnetic field in time 25. If we advance in time to panel B, we can see that there is some waves that are appearing that we can see
Yes.
it because there is blue and red. We have some oscillations.
Yes.
Um,
Yep.
the wave that we will focus is in the one that has the green cat
Okay.
line.
Hmm.
And in panel C, we can see that that wave is still increasing and developing. Um, and it's clearly that the wave is following the magnetic field lines.
Huh.
Uh,
Okay.
in the second row, we can see that in panel E, This increase of electron anisotropy in the region of the where the wave is evolving.
Yes.
The same in panel EF. Uh, so it's very possible that this electron isotropy is feeding the free energy that the wave requires to be produced. And we can see that in that region also there is some velocity shears
Yeah.
due to of the large scale like
Mm.
vortices. They
Uh-huh.
produce like velocity shears in that areas where the anisotropy is being produced. So we propose that the velocity shears are producing this an electron anisotropy,
Okay.
and this electron anisotropy fits the wave and produce the wave that we are interested in.
Cool.
Also in the third row, the we can see that the wave is quasi-parallel to the background magnetic field. Uh, um, so
Okay. Okay.
so the wave is propagating with the quasi-parallel. So yes, so it's more or less between 18 degrees, more or less. So yeah.
Yeah, thereabouts. Yep.
Why we are interested in these waves? We will see that these waves that we are trying to characterize and study that are being produced by the turbulence um, will have a lot of different process that will end on the formation of the electron-scale magnetic hole.
Cool.
So this is very interesting because the nonlinear interaction with the wave at different and between different cross-scale interactions in the turbulence
Hmm.
is we will see that is able to produce these coherent structures.
Nice.
So
Nice.
if we want to characterize the wave, we now we will go to figure 3, where we plot in that green line cut that we did,
Yes,
we plot different parameters
I'm with you. Hmm.
of the plasma.
Hmm.
So we can see in panel A, we plot the different components of the magnetic field. The magnetic field is, in this case, mostly in plane direction. So um, that's why the wave can be propagated quasi-parallel to the background magnetic field.
Uh-huh.
Uh, we have also that in panel V, we have the high pass filter components in the coordinate system aligned with the background magnetic field. Uh, we can see they're very sinusoidal and
Yeah. They kind of come together.
in panel, well, of course, the component aligned to the background magnetic field is not plotted because it's zero because of the magnetic field has the divergence is zero. So
Yes.
the panel C, we have the density
Cool.
fluctuations.
Okay.
I mean, we can see there is no much fluctuations. It's like
Yes.
so it's an incompressible wave. In panel D, we can
Okay.
observe the
Okay.
electron fluid velocity different components in the system like longitudinal normal to the wave,
Mm-hmm.
and in the out of plane direction, we can observe that in the direction of the wave there is no much fluctuation. It makes sense with the incompressibility
Right. Right.
of the perturbation. And of course, in panel E, there is the ion fluid velocity components, and they doesn't interact. So in a is a we will say it's a wave that doesn't only interacts with the electrons.
Yes.
Um, in panel F, we did uh, like the Fourier spectrum of the
Okay.
wave.
Okay.
Uh, in that cut, we can observe that more or less the wave number is 0.8
Mm-hmm.
with respect to the electron inertial length. And in panel G, we have we plot in the that yellow part of panel V, that section that we highlighted in panel V.
Yes.
We plot an autogram of that section,
Yes.
and we observe that the wave has more or less circular polarization and is clearly also right-handed, where it starts in the red point and it ends in the blue. So it
Ah,
goes.
okay.
And the background magnetic field is in the out of plane direction.
Uh-huh.
So
Turbulent. Okay. Cool.
now, well, all these characteristics are very consistent with a Whistler wave.
Uh-huh.
Um, with this, like a clear, very like clear example of Whistler wave. Now, if we try to
Okay.
um, compare these observations with a linear solver, we used a linear solver using like mean parameters
Okay.
we of the of that cut. So we did an average of the different plasma parameters in that cut. We
Okay.
put it in the linear solver and we obtained panel H2J.
I'm with you.
That's different isocontours of the frequency, the real part of the frequency, the imaginary part of the frequency, and the polarization given by the linear solver
Gotcha.
with respect of the wave number
Uh,
and the angle between the angle of within the propagation of the wave of the background magnetic field.
yes, I'm with you.
We can observe, we plotted between 18 and 30, that's the angles that we saw that has
Hmm.
the propagation of the wave in the simulation.
Uh-huh.
Um, we can see that the real number, we the those that vertical line, black line,
Yes.
is the wave number that we obtained because of the Fourier spectrum, Fourier transform.
Right up here.
And
Uh-huh.
yes,
Yes, right
in
here. Uh-huh. And F's.
so
I'm with you.
we can observe that the frequency is around zero point 0.4 with respect to electron radius, is in
Mm-hmm.
the typical characteristic frequency of Whistler waves. Um, we
Cool.
can observe that just this is very important in panel in the next panel. We can see that
Uh-huh.
just in the wave number that we saw in the simulation, there is an instability, and
Okay.
so there is a wave that is producing that instability, and the wave, the imaginary term of the frequency, it match with the characteristic times of the
Yes.
of how the wave is produced. So the wave is produced around in in a scale time of 100 with respect to electron radius, and
Huh?
is more or less in the scale of we can observe in the simulation. So it's very we sustain that it probably the anisotropy
Yes.
because of electron synchrotron instability because of the anisotropy
Yes.
there is that is producing the wave as we can see linear solvers sustain our idea. And of course, that anisotropy is produced because of the electron velocity shears that are produced because of the larger scales vortices. And that's why how the energies has been transferred from these large scales down to these
Electrons.
kinetic scales.
Yes.
And the polarization also is completely right-handed and very circular. It's mostly in one, between 1.1, 1.4. So
Yes.
it matched with the
Okay.
simulation.
Okay.
So during the paper,
Okay.
we will treat this wave as a Whistler wave. It has all the characteristics. So these figures have been basically to understand how the wave is produced, to propose some mechanisms how the wave is produced from the turbulence, and to understand the characteristics.
Good.
Now we will follow the developing of this wave until it gets produce the electron-scale magnetic hole.
I'm with you.
So if we continue to figure 5,
Okay.
we will advance in time.
Okay. Now we're gonna do a conversion.
Yeah,
We're gonna do a conversion.
a conversion.
Okay.
Okay, if we advance in time, um, we will see in the first, as before, we have the columns with different times and the row with plotting different parameters.
Good.
In the first row, we have the angle between the background magnetic field and the wave direction. The second one, we have again the high pass filter magnetic field in the out of plane direction.
Yes.
And in the third one, we have the high pass magnetic electric field
Electric field.
in the longitudinal direction.
Okay. Okay.
So in the first row, we between panel A and D, we can observe that the now the wave, well, that cut is in the place where the wave is propagating. The
Mm-hmm.
wave is propagating now because of the background is very inhomogeneous. It's propagating to a direction that is uh, with has a high component of the out of plane magnetic field. So the direction of the wave and the magnetic field start to be instead of quasi-parallel, quasi-perpendicular. So it
Okay.
has a high angle between the magnetic field and the wave direction, and that's because these
Okay.
streamlines that are the streamlines of the total current of the
Okay.
plasma.
Uh-huh.
We can observe that these vortices are increasing the magnitude of the magnetic field in the out of plane direction. And that makes that the
Yes.
angle of propagation of the wave and the magnetic field increases.
Yep.
Um,
Okay.
and next, if we go to between panel E and H, in panel E, we can observe that the wave
Ooh.
it has like a bubble
Yeah.
structure.
Yeah.
It's not as before that we have like a clearly sinusoidal and very like book
Mm-hmm.
example of wave, very beautiful. Now it has like a very different type of structures.
Mm-hmm.
And if we do a zoom of there, we can see that we plot the streamlines also of the high pass filter electron current,
Yes.
and those are actually not longer like the wave the Whistler wave that we saw before.
Uh-huh.
It's like a train of vortices
Yes. One, done.
that goes in different directions. So there is vortex in one direction, decreasing the background magnetic field, and the other direction, increasing the out of plane magnitude of the magnetic field.
Yes.
We can see in panel F that later these vortices will merge
Merge.
together.
Yes. Mm-hmm.
And in panel G, we see that these merged vortices
Oh.
merge into this decrease of magnetic field magnitude, this dip of magnetic field
Uh-huh.
that will evolve, as we see in panel H, to the magnetic electron-scale magnetic hole what that we saw before. And
Yes.
the electron-scale magnetic hole has actually the same scale as the length of the wave that
Oh, that we saw.
the
Yeah.
Whistler wave, the initial Whistler wave
Okay. Okay.
that we characterized.
Yes.
Uh, and in the third row, we have also that in
Okay.
that region, we have a longitudinal component of the electric field that we
Yes.
didn't have before. So
Right.
there is some electrostatic fluctuations that are occurring now.
Ooh, yes. Good.
Um,
Decrease.
and of course, in panel L, these electrostatic fluctuations, when the magnetic hole is fully developed, they just disappear with the turbulence.
Correct.
Uh,
Right.
Yes. Now, okay. So
Develop.
we saw that,
Okay.
okay, there's this wave. There is evolving in a weird bubble-shaped manner with these electron scale vortices. There is now um, electrostatic fluctuations that are appearing. And we know that this magnetic hole is produced because that merging of these structures, vortice structures that have been produced. Now we will understand how this happened because we had the
Ah.
Whistler wave and now this we have this different stage.
Ah.
We will fill the gap between that. And the thing is that there is a mode conversion between the Whistler waves and Bernstein type of waves. And we will claim that this mode conversion is because as the plasma background is very homogeneous and now the angle of propagation of the wave because of the magnetic field is increasing in the out of plane direction, the angle of propagation between the wave and the baromagnetic field is increasing.
Yes.
This this Whistler wave acts as an antenna that drives
Ah.
the generation of a Bernstein wave. And this Bernstein wave, of course, the Bernstein wave propagates in the perpendicular direction with respect to
Yeah.
the background magnetic field.
Gotcha.
So because of the background is changing, that Whistler wave drives a new mode of propagation that will be the Bernstein one, the
Cool.
electron Bernstein one. So yes,
Very
and
cool.
we will see later that the
Huh.
Bernstein, because of these electrostatic fluctuations that appear in this Bernstein mode, these electrostatic fluctuations will induce these structures, vortice structures, that will at the end be responsible for the merging of the vortice and the producing the final electron scale magnetic hole.
Cool. I'm with you.
So that will be like a general
Yep.
overview. And if we go to panel 6, we can see how this mode conversion occurs.
Okay.
Um,
Uh,
so in panel 6, there is a plot between, in figure 6, between panel A and D, there is a plot of the different components of the high-pass filter
yes.
electric field in the longitudinal normal coordinate system. Um,
Yes.
we have a plot also of the different components of the background magnetic field, and we have an spectrogram of the longitudinal high-pass filter component of the electric field
Yes.
and of the high-pass filter magnitude of the
B.
magnetic field.
Yes.
So
Okay.
those are the different plots in the panels, and
I'm
we
with
can
you.
see in panel A,
Okay.
just when in that time we have the Whistler wave, we have that there is there's no longitudinal fluctuations that are very, it's
Right.
like noise.
There's just noise. Yes.
Yeah, and then we can clearly see that there is some fluctuations in the out of plane direction,
Mm.
but mainly the background magnetic field is only in the longitudinal direction.
Yes.
That's why the in this case
Black and red.
the the wave is propagating quasi-parallel.
Uh-huh.
Uh, then we can also observe that there is also in the spectrum we doesn't see very much longitudinal fluctuations of the electric field.
Mm-hmm.
So, and we observe clearly the Whistler wave fluctuations. With these horizontal lines, white lines, are the different um, harmonics of the
Ah,
Whistler.
okay.
So we have
Okay.
the first, the second, and the third harmonic of the Whistler wave number.
Yes.
So we have the Whistler wave in the third line, the first harmonic, of course.
Uh-huh.
That's the wave number that we predicted before. And in panel V, now if we advance in time,
All right.
in the time where we see that before, just
Ah,
before start seeing these bubbles, we we see that there is a huge longitudinal electric or significant longitudinal electrical fluctuations. So
yes.
now we have these electrostatic perturbations.
Yes.
Now we clearly see that these electrostatic perturbations just appear where the
Ah,
out of plane background magnetic field
oh.
just overcome the longitudinal component of the background magnetic field. So
Uh-huh.
it's when it starts from the quasi-parallel propagation to the quasi-perpendicular propagation.
Yes.
And we can see that there is now appears like this longitudinal perturbation of the electric field
Yes.
in harmonics of the Whistler wave number.
Right. Right.
Yeah,
Yes.
well,
Yes.
that the harmonics of generation harmonics is typical of a nonlinear process when we have some wave mode conversion because of nonlinear
Mhm.
effects of the waves. And of course, in this case, if the background is inhomogeneous, the mode conversion will generate not longer harmonics of the Whistler. It
Right.
will produce harmonics with the wave number, but harmonics of the Bernstein mode. In this
Cool.
case,
Yes.
because of different characteristics. The same happens in panel C. When we continue the developing of this mode.
Let's move on.
But in this case, we can observe that the vortex is start formatting. We can see that the dip that we can observe. Well,
Yes.
that's why we have that high intensity in the spectrum of the magnetic field because it's not longer the Whistler wave that it disappear.
Right.
Is is catching the dip of the magnetic field that is at the same scale of the of the Whistler wave number. So the
Okay.
div is
Okay.
it has the same length of the Whistler wave that initially produced this drive this mechanism.
Cool.
And in panel D, the electrostatic longitudinal electric field fluctuations disappear, and we
Uh-huh.
just have the a huge tip of localized tip of the magnetic field. That
Yeah.
is the electron scale magnetic hole fully developed. If we do in panel C, if we just take the part before the magnetic field,
Okay.
in panel in the go a little in the panel above that, we have a yellow part just before.
Oh yeah, right here.
Oh
Hmm.
yeah, that
Yep.
right there. We take that part,
Yes.
um, and we can do another gram of that part. That is where the electrostatic fluctuations are developing.
Yes, they are. Okay.
And if we do another gram in panel E and F,
Yeah.
we can observe in panel E that there is not much normal fluctuations compared to the longitudinal fluctuations, and it's mostly linear some
Yeah.
way. Of course, is not exact, but
Okay.
it tends to that. In
Mm-hmm.
panel F, we have the same with the out of in the audiogram between the out of plane direction and the longitudinal one. The green arrow is the direction of the background magnetic field. We
Yes.
can see that the longitudinal fluctuations in direction of the wave are highly perpendicular.
Cool.
So it has the all the characteristics of a Bernstein
Yeah.
electron Bernstein mode.
Nice.
Uh,
Beautiful.
in yes, now okay, so now we characterize the Bernstein fluctuate the mode conversion between the Whistler and Bernstein
Yep.
propagation, and we notice that we have this electrostatic or longitudinal electric fluctuations.
Uh-huh.
Now we will see how these longitudinal electric fluctuations will produce these vortice structures that will end in the electron-scale magnetic hole. So
Cool.
as we go to panel 7, um,
Okay.
okay, so as before, we have different columns, different times, different rows, different parameters of that plot.
J.
In the first row, we have the high-pass filter of the normal component of the electron current.
Uh-huh.
In the second row, we have the high-pass filter or the longitudinal component of the electron current. And in
Yes.
the third row, we have the normal component of the high-pass filter electron current produced by the B cross drift. So,
With him.
and we are using this will be basically the current produced by the B cross drift with the taking the high-pass filter of the longitudinal electric fluctuations.
Okay.
So, okay, in the first row, we observe these like filamentation of the current. So we
Uh-huh.
have these filaments of the current that are normal to the wave direction.
Yes.
Uh, in panel C, we can see that observe how this filament change of the structure, and we can see these big blue and red points
Yes.
where the vortex is merging, and of course, indeed, this disappears these
Boom.
structures,
Right.
and that's the point where the electron scale magnetic hole
Version.
already formed.
Yes.
In panel E, we can observe that in the case of the longitudinal electric current, electron current.
Right. Yeah.
It has like a shape like this. So there is a current going to this direction and this direction.
Okay.
So those currents, this normal one to the longitudinal one, if we sum each other, we will have the shape of the vortices,
Cool.
the electron ring currents that produce the vortices that we saw before, that produce those type of bubbles. This and we observed in panel in the third row that between panel I to L that that there is this current produced by the B cross drift with the electrostatic perturbation.
Okay.
We if we compare the third row with the first one, we
Yes.
observe that
Yeah.
they match very well.
Yes,
So there's probably some correlation between each other.
definitely.
And actually, there is.
Mhm.
We will see later in this following plot. But before seeing that there is a correlation, what we okay, well, go to the figure 8
Eight. Okay, I'm with you
or
on this
uh,
one. Okay, figure eight.
to explain the mechanism. Nine,
Nine.
figure 9. Yes,
Nine.
there's
The
yeah,
illustration. Yes.
yeah, the illustration to see better. So.
Okay.
Okay, we observed that these filaments will be the red and blue zones will is an illustration of this electron um, electron current filaments.
Yes.
We observe that will be they will change from direction, like from this direction to this direction, and
Mm-hmm.
that come on.
Mm-hmm.
And that produced that structure, that zigzag structure of the high pass filter of the electric current.
Okay.
Um,
There's our
and we observe that this
okay.
current is produced because if we take those arrows that are going down and up,
Yes.
are the longitudinal electric fluctuations, electric field fluctuations.
Uh-huh.
So those longitudinal electric field fluctuations, if we do the vectorial product with the background magnetic field,
Yes.
uh, they are producing because of the velocity drift, where they are producing these currents that are fluctuating that produce that zigzag, and that zigzag electron current is have the shape that produce that vortices that have the scale of the wave,
Okay. I'm with you.
and those vortices are the one as we saw before produce a magnetic
Uh-huh.
hole, electron-scale
Uh-huh.
magnetic
Yeah,
hole.
we saw this in those earlier plots.
Yeah.
Yeah. Okay.
And we can observe actually in figure 8 that there is a very good correlation between the normal components of the electric field current and the the normal component of the electric field current of the E cross V current that we talked before.
Uh,
So
okay.
where we plot the Pearson coefficient, we can see that the Pearson coefficient of correlation is very high. So
I'm
is a
good.
very good correlation between
That's
those
pretty
and
good.
for the different times.
Yeah.
Of course, there is some
Noise.
there is no perfect matching. There is some currents that we are not considering.
Right.
As we said before, in the first plot, when we characterize the electron-scale magnetic hole, we plot the different currents. The E cross V current, we plotted the pressure current. We saw that the E cross V current is mainly sustaining this electron-scale magnetic hole.
Yes. Yes.
That component of the generalized Ohm law. But of course, there is some inertial terms and kinetic effects that we are not considering that in that formulations that are having some effects. So that's why there is not perfect matching.
That's seeding the noise there. Yes. Okay.
Yes. Well,
That's a
so
trend
with
is
that,
there.
with that, we will say that we end like the story.
Okay.
Uh, so if we do a review of this,
Sure. Yeah.
I'm
It's a
yeah, I
summary.
think I think in figure. Oh no no no, there is another figure, but I didn't put in the paper. I have in the
Oh.
presentations.
Oh well.
Yeah, but
Sorry.
okay, it's a review of the process. But I will say the review. We go step by step. So first, we have the large scale turbulent velocity shears are produced because of these large scale velocity like vortices.
Yes.
These velocity shears produce the electron anisotropy
Yes.
that feed the wave. So the wave is increasing because of the electron synchrotron instability.
Uh-huh.
That produces a Whistler wave um, that is propagating quasi-parallel with respect to the background magnetic field,
And
but because of the large-scale currents of the turbulence, that currents increase the background magnetic field in the out-of-plane direction, and that inhomogeneity of the background magnetic field
is what
produce a mode conversion between the Whistler and the Bernstein wave.
got it. Uh-huh.
Um, So the Whistler drives acts an antenna and drives the conversion and the produce the
Cool.
harmonics of the Bernstein wave that
Yes.
has in harmonics of the Whistler wave number that we saw.
Started with. Mm-hmm.
Those Bernstein-like modes have a longitudinal electric field component.
Equals.
So that the longitudinal electric field component, the Bernstein wave, interact with the background plasma, producing A cross B drift
Yes.
currents. That currents in turn produce the vortices,
The voice.
electron-scale vortices, and the
Huh?
scale of the Whistler wave. That at the end will end merging
Merge.
and will produce the magnetic hull. As
Very
you can
cool.
see, yes, there is a lot. It doesn't also only produce dips. The vortices produce dips and peaks of the background magnetic field.
Very cool.
Those dips, two of those dips are merging, and the rest will disappear.
Dissipate. Yeah.
Also, the peak dissipate with the turbulence. They disappear also.
Uh-huh.
Um, it will be very interesting in the future to understand why exactly those vortices merge,
Yes.
why they stabilize in the baromagnetic field and the other doesn't stabilize. Some reason can be that maybe the deep of the magnetic field needs some to to get through some threshold. So under that threshold of background of degrees of background magnetic field,
Yeah.
the magnetic hole doesn't stabilize and doesn't appear
Oh.
over that, or maybe it can be a possibility.
Yeah, yeah,
We
yeah.
we it's hard to say. But that stability and how it merged can be interesting to future works. Also, to understand it's possible that this same mechanism can produce peaks of magnetic peaks that are instead of magnetic holes that are dips, like localized dips of the magnetic field,
Uh-huh.
those are localized
Oh,
increases of the magnetic field.
yes.
So those are very interesting. But at the end, the importance of this study, more than the specific mechanism, that is very interesting to see that the cross-scale interactions at the wave and the wave can produce electroschematic holes. But the big point is that we demonstrate that even if this is possible not the only mechanism,
Or
the turbulence can drive the generation of electron-scale magnetic holes. So the turbulence is the instead of maybe mirror instability, electron mirror stability, other process, it
right.
can be just the turbulence who are producing these magnetic holes that are usually observed um, in different environments. In this case, in the magnetosheath.
Oh,
Um,
yes.
of course, this simulation, the future can be done for parameters that are more correspond more to the different environments as the solar wind or other space
Right. Right.
turbulent environments.
Uh-huh.
Um, and also an extension of this work that will be really interesting is to do the 3D simulation.
I was
Of
gonna
course, it's more
say, yeah, yeah,
expensive.
yeah. Mm-hmm.
Yes, because in the 2D simulation, we have the 2D structure of the hole, it's only a dip. But in the 3D one, the magnetic holes have like a cocoon structure. It can be produced maybe because of different instabilities. It's a very interesting case to analyze. And that we are thinking to work in that in the future in collaboration with Giuseppe. Um, and this work, we are very proud of this work because also it ends with this like trilogy of papers, we'll say, that Giuseppe was doing about starting from the largest scale magnetic hole one,
Right.
the near ion scale, and
Uh-huh.
the sub-ion
Final
scale
scale. Mm.
magnetic holes. And in those three cases that are observed usually in these turbulent plasmas, we can see that the turbulence can be in fact um, uh, the factor that drives the
Yes.
generation of magnetic holes. And this also is very interesting because It also uh, collaborate to explain how and there is an energy transferring from the larger scale to the small scales.
Uh-huh.
The magnetic holes, it believed that they can also impact in dissipation of turbulence and
Yes.
other
Yes.
uh, phenomena that are occurring in the turbulence. So
Okay.
uh, it's
Cool.
very important to consider that. Yes. So that will be a general overview of this paper. Um,
All right.
that's it. Yeah.
Joaquin, beautiful work. Beautiful work. And I want to thank you so much for walking us through your very awesome article.
Thank you. Thank you very much for giving me the opportunity to present this.
Sure.
Yeah.
And you touched on it a little bit there on future directions and sort of the globals of the three different scales going on and where you're going. Let me ask one question. So on these simulations, right, we were doing an electron to ion mass of 100. Do you
Yeah.
think if that number got larger, that the amplitudes of those fluctuations would get larger?
If the number gets like more realistic, you say.
Yeah, let's just phrase it that way. What if the number got closer to 1800 or so? What kind of changes might one expect on that?
Well, I think that the changes will say, for example, in the paper that of Giuseppe for near scale one,
Uh-huh.
we see that near ion scale one in that case is very close to an subion scale one because of the different mass ratio.
Okay.
So,
Okay.
I
Yeah.
mean,
You would
yeah, so
trade.
probably the that different in the other mechanism of the other paper, the electrons, the near ion scale magnetic holes are produced by a Kelvin-Helmholtz instability and etc. This in that if we put more realistic, I think that just the scales will be more differentiated.
Yes. Yes.
Yeah,
Yes.
between there will be more difference between those, but at the end probably the general qualitative characteristics
Are going to
wouldn't
be the
change very
same.
much.
Correct. Yep.
Yeah.
I agree. It's just the amplitude of them will change, I think.
Yeah.
My guess. Very cool. Very nice. Well, it'll be really exciting to see this over the next couple years develop as we move into some of those 3D simulations and tying them all together. So very nice.
Thank you
Be
very
exciting.
much.
Yeah. And that will do.
Yeah.
And that will do, everyone. And I hope this made your astronomy day, your MHD picks day a little bit better. And we will see you on the next one. Bye bye.
Thank you. Bye bye.